Hello, and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening. My name is Julie Tomei, and I am joined by Dr. Elena Hyde. Hi, Elena.
Hello, hello. So happy to be here.
Okay, glad to have you. We are broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time, that being currently 1 a.m. Universal Coordinated Time. On YouTube at the York U Observatory, and in concert with our online public viewing program run by the Observatory team. You'll also find us now wherever podcasts are distributed. To navigate to the live show or to find out more, check out our website at www.yorku.ca/science/observatory and follow the links to OPV for online public viewing, and join in the live chat on YouTube. For any questions or comments you have of our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. And you can connect with us on Instagram at our handle at York U Observatory, or Facebook at Allan I Carswell Obs. All of our programs are free, but should you wish to make a donation, we certainly won't say no. Please head over to our website, www.yorku.ca/science/observatory. We'll be monitoring the chat room for questions to post content. Currently, it is clear. It's been nice and clear for several days now.
Oh yeah,
Uh, yeah, so we'll be seeing some live images from the telescope tonight.
absolutely. Not just any
Yay!
live images. We will be looking at stars.
Stars. Well, that makes sense.
We're actually going to be spying on a research observation for an exoplanet. And of course, we'll probably talk a little bit more about this once it gets going. But once they connect it up, when you look for exoplanets, you don't look for planets, you look for their host stars. So, of course, we can't do anything without beautiful starlight to examine.
Yes, absolutely. And the reason we are being very enthusiastic about stars will become obvious very shortly.
Well,
Um,
I think, Julie, it's only natural that, when you start reading lots of things online, you can get sort of obsessed with certain stars and even superstars, and you just want to follow and learn everything about them. So we're
Absolutely.
gonna Anyways, no, it is great because there's definitely some very good puns to be made here. I don't think I'm awake enough to make them all, but just feel free to substitute superstar in wherever you listeners feel that it is appropriate.
Yeah. Um, so shall we dive right in then?
Yes. So for this week in space and astronomy history, as I told Julie earlier, am planning to majorly because I actually found some really fun stellar stuff from my own library, and I thought, I don't do enough papers. I don't talk enough about papers that I've actually written. Maybe I should fix that. So please keep in mind that this week in space and astronomy history from 2015. This is maybe not history to everybody, but it is history to me. So therefore, I'm going to include it. October 25th on 2015, there was what I thought was at the time was a very lovely paper published called Significant Populations, Lessons Learned from the Sagittarius Stream. And this is a stream of stars. So that's why I said, yay, stars. I mean, obviously, superstars. These stars are not technically in the astronomical definition of superstars, I must point out. They tend to be older, smaller stars that are left over from an earlier time in the history of our galaxy. And our galaxy being the Milky Way, and being pretty much all the stars you can see when you look up at the night sky, provided you're not in downtown Toronto staring at a spotlight. But if you can see all of those stars, they're all part of one large, complex, very messy system that's called the Milky Way galaxy. And if we want to get out into other galaxies, then we need to go much, 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 much farther away. And we can just barely, of course, see the Andromeda galaxy here in the northern hemisphere. In the south, you have the Large and Small Magellanic Clouds, which are sort of messy satellites to our own Milky Way. I always like to remind people that Milky Way, as a structure overall, kind of bears a resemblance to a very, very, very flattened fried egg. Um, but it has a halo, and the halo is this giant sphere that it sort of encompasses the whole region around the galaxy. And we can see that there's some kinds of structure, still remnants out there in the halo. So back in 2015, which feels like it was a million years ago, um, and it wasn't. Um, but back in 2015, I actually was living in Australia, and I was, I believe, now I have to count, I think this was either the year or the year after I became an Australian citizen. And I was studying with the telescopes there at Siding Spring Observatory, looking at individual stars. And at the 1 meter telescope, we have a lovely setup here where we can do spectroscopy, I should say, spectroscopy with our spectrograph, and then switch to other instruments. But the light coming in at the moment, we have what's called one optical pass. So when the light comes in from the telescope, we can point at one large field of view at a time. However, in Siding Spring in Australia, they had what was called 2DF, and it was a 2DF robot. And 2DF stands for 2-degree field of view, which sounds huge until you realize that you're not actually seeing it at all. What you get is you have a robot that crawls around the 2-degree field of view inside the telescope and places little fiber optical cables. And there's 400 of these little tiny fiber optical cables that are sort of flexible, and they stick into a plate. And you place them around wherever you have configured your star locations to be. So in theory, if you used all of them, you could get 380, so minus the calibration fibers, 380 stars at one time, just to run into and grab their spectra out of, for example. So it was used for surveys. You don't get the beautiful pictures that we do from the 1 meter telescope, like those ones that are showing for online public viewing now. Whole pictures that show galaxies and large fields of view all at once. We couldn't do that out there, but we could get lots and lots of measurements of individual stars. And so actually that's what I did for before 2015. They let me run loose on their telescope, and I got about 20,000 stars. I would say one by one, but it was, probably anywhere from 100 to 300 at a time. So it was a pretty good deal. Now, these stars, I would like to point out, they're interesting in lots of different ways. So if you've heard about stars in the sky, well, you've probably heard about our sun. It's like, okay, well, so what is it out there? It's all hydrogen and a little bit of helium. Sometimes there are small traces of other metals. If the star has formed more recently, it'll have more of the metals from stars that have exploded in its formation. So the idea is it gets what's called enriched. Young stars die, they explode, lots of stuff goes out there. And when it's anything other than hydrogen or helium, generally we just call it a metal, and we look for that kind of enrichment to see, is it a young, new formed star, or is it an old ancient star that could have been around since the beginning of the universe? And in theory, there's actually a fun class of stars called the first stars. So there's a bit of a contest still ongoing to find the lowest metallicity star. So if you could find a star with the lowest metallicity, you would also have to be able to measure exactly zero. So there's two problems there. So anyways, this little stream from 2015, not to tell you too much about everything that, this was a stream of stars in our own Milky Way. and it's lessons learned from the Sagittarius stream. So it was about one particular dwarf galaxy that came a little bit too close to the Milky Way at some point in the distant past. And when things get too close to gravity, they tend to get broken up. So this could happen to you if it's a black hole, very compressed sort of gravity. But if you are an entire dwarf galaxy, just being near the Milky Way might be enough to start making your stars sort of fall off. So the stars at one end, whatever end is closer, get pulled more than the stars at the farther end. And as the galaxy, the dwarf galaxy moves, the stars kind of just get spread out and smooshed across this giant stream. So the stream today was found to have wrapped all the way around the Milky Way. So the Sagittarius stream is a really interesting one because it basically goes around the fried egg on the outside. So if you're thinking of fried egg, you've got the plane of the fried egg, and then you've got 90-degree angle to the plane of the fried egg. So it would be going up at almost a 90-degree angle, up and over and around. So it's going through a large amount of the halo, which made people really, really interested in trying to use those stars, physical stars, as a proxy to be able to actually discover things about the dark matter halo of the Milky Way. There's a whole set of papers about whether it's triaxial or not. I'm not going to touch that with a 10-foot pole, but the stars themselves, though, that is something we can see. So that's something like, these are measurable, these are quantifiable. We can see them, we can look at their structure, and of course we can measure their spectral composition. So actually this is timed really, really well, because if anyone is live right now, they have just switched to a stellar view for the imaging tonight over on OPV on the YouTube channel. So if you're listening to this later on, you might want to go check out that recording. You will get to see a beautiful star field focused around the host star for GPX-1b, the exoplanet. So looking at your fields of stars, you can try to untangle other things. And this is one of the great things about stars, because they are so useful as proxies, as probes of different things. We can use them in their wobbles or their dims in light to identify exoplanets. We can use them and their motion and their velocity and their position to identify how a dwarf galaxy used to look, which is what this was. So we tried to unwind the Sagittarius stream that we see today and see if we can wind it back up. Like, can we just reverse the velocities and see what kind of object this used to be back in the early formation of the galaxy? And after many, many measurements, what we found was the earliest, sort of explanation actually seems to be kind of the correct one. It's that at ancient points in the Milky Way's formation, before the Milky Way was the Milky Way, when it was just a collection of messy small galaxies and maybe some sort of center, there was a kind of spherical blob of stars that used to be the Sagittarius dwarf galaxy. And it got too close. And that's what has been gradually stripping its stars off this whole time. And that's what has formed the beautiful stream that wraps all the way around the sky. And because these are stars and because they're very old, they're also very, very, very dim. And one of the great things about this structure is that it is hidden by being in our galaxy and being very faint. So actually to find it, and to actually identify what's really there, as opposed to just other halo stars or other random things that might be in that direction, you have to have points of identification. And that gets you to chemical tagging, which probably is something for another talk, but it's using the spectra to kind of make a fingerprint of the star. So nearly on this day, back in 2015, I had a big pile of data that had managed to prove that, in fact, the progenitor of the Sagittarius dwarf was likely actually not rotating, which sounds like a negative, but it was really fun. And I thought it would be a little bit of a lessons learned day in history. If you do happen to get a gift of 20,000 or so more spectra, you can start to do some really interesting statistics with it. So that's what I would advocate for. And of course, that's probably where I'll end that little story.
Elena, that is the coolest thing I've heard all month.
That's the only thing you've heard all night.
No, not all night, all month.
Oh, all month. Okay. I was like, we haven't covered anything else.
No, I know.
Um,
That's why I went for a
I'm
longer
glad. I
period
thought it
of
was really
time.
fun.
That is so cool. I went and was like, what will happen if I Google Sagittarius stream? It's got these great illustrations that I had no idea this thing existed.
Well, and just as a little shout out, one of the reasons why I brought this up today, as we're approaching 2025, 10 years later, on the 60 centimeter telescope at the Allan Carswell Observatory, we have a new instrument called Quail. And Quail has had a very interesting history that we shouldn't get into here, but it has the ability to pick out streams, and especially the gas component of streams. And one of the targets that we can look at with the Quail on the 60 centimeter over at the Allan Carswell Observatory is the northern hemisphere portion of the Sagittarius stream.
That's so cool.
I know. I'm really looking forward to it. We're actually just trying to get, I suppose, second light, get it back up on the sky right now. So it's very exciting times.
Wow. Okay, so there's going to be like more data to add because you, for this paper, was all Southern Hemisphere stuff, I'm assuming. That all
No,
the
actually,
Northern
I did.
Hemisphere stuff?
When I in 2015, I did not have access to the Allan Carswell Observatory, unfortunately. So I had to get some data from France. But it
Okay, so
actually,
you
I
had
do
Northern
have
Hemisphere
northern.
stuff too.
Yeah, I do have northern hemisphere components that we can match to. And our follow-up objects for checking individual star membership can be done with the 1 meter spectrograph.
It's really exciting.
I know.
Woo.
It's going to be so much fun.
Stay tuned, people. Exciting science coming this way.
And history too.
Yes. All right.
Speaking of exciting science,
Yes. Okay, so we're going to go to October 15th, 1909. Um, and this is we used to do a lot of like the birth of such and such a person. And maybe we haven't done as many recently. But we're doing two of them tonight. So October 15th, 1909, Jesse Greenstein was born. He was born in New York City to successful immigrant parents who indulged his interests in astronomy, radio, and science. And he started high school at age 11 and entered Harvard University at age 16. So, kind of a smart guy.
yeah, that's
So
pretty smart.
yes, you're pretty smart, right? Starting university at 16. So that was in 1926. While he was there, he became good friends with Cecilia Payne because this was the Glass Universe era still. Um, he earned his BA in astronomy in October of 1929 and stayed on one more year to complete a master's degree. There was this little stock market crash that happened back then, and that pulled him away from astronomy for a few years because he had to go help out with the family business, make sure that everything was running okay on that side of things. But once he was satisfied that the business could go on without him, he returned to astronomy, and that was in 1934. Despite Harlow Shapley insisting that the field had advanced too much during his absence for him to catch up. But I think he managed to catch up. He married his high school sweetheart, Naomi Kitte, the same year. And she was passionate about art and the theater and life in general. At Harvard, he studied the scattering of light by interstellar grains, and he was awarded an NRC fellowship in 1938, which he took to the Yerkes Observatory, where he started a collaboration with theorist Louis Hennier. Hennier? I don't know. one or the other, possibly neither. Sorry, Louis, if I'm mangling your name. He also started studying stellar spectroscopy and did the first analysis of the peculiar hydrogen poor object, Upsilon Sagittarii. He and Henier worked on optics during the Second World War and became interested in developments in the field brought on by the war, such as infrared detectors, photomultipliers, sensitive radio receivers, and rockets. He was invited to Caltech in 1948 to build their department, and use the 200-inch Hale telescope that was about to be complete, which was at the time the largest and most ambitious telescope project. He built that department by hiring the best theorists worldwide and teaching them to become observers. And he built a postdoctoral program around stellar abundance determinations. Greenstein continued his research of dust with Leverett Davis, and in 1951 proposed the magnetic alignment mechanism to explain interstellar polarization. His research then turned towards white dwarfs, blue subdwarfs, and the nuclei of planetary nebulae. This work led to obtaining spectra of faint blue objects with weak, broad emission lines that were not readily identifiable, and those turned out to be quasars. He pushed for funding of national observatories like the NRAO and was part of the founding of the National Science Foundation, and was part of numerous committees and etc. Lots of honors throughout his career. He died on October 21st, 2022, just a few months after his wife did.
Very, very achieved life here, as you say.
Indeed.
Sort of high achiever all around. And I do love how it was, even in what was that, 1934, 30, yeah, 34. So you said he was
Mhm.
trying to come back, and they were like, oh no, no, the field's advanced too much, which is still what they'll tell you today, is
Yeah.
that things have changed so much. It's very hard to come back. But a lot of people have left for a few years and come back. Actually, and a lot of them to make money, myself included. So it is possible. But yeah, it is funny that it's like this was the case even back in 1934.
Yes. Imagine telling a guy who started university at 16, no, no, you won't be able to keep up.
Yeah, well, I mean, imagine telling that to anybody, really, because it's just
Mm,
like, hey, if as long as they understand the difficulties, if you want to give it a go, like, go for it. Um,
true.
you know, uh, it's not like he's applied to go into, I don't know, welding or something. I completely different. Um, but yeah, even if you do, it's like, hey, do you think you can go for it? Go for it. And he totally became, as you said, hugely, hugely successful. And we've talked so much about spectroscopy, but this is one of the people who came up with a lot of the analysis techniques that we use today. So good for him, and good for us, actually.
Yeah. Sounds like an absolutely um very accomplished, very involved in all sorts of things. A lot of this information, actually all of this information I got from his obituary. Um Sounded the end was like about how he was as a person, and he built that department at Caltech and really made sure that the folks there were good. Like not good in astronomy, but like good, like how you doing? Do you have any problems, astronomy or otherwise? You can, my door is
Yeah,
open.
a healthy research environment is so, so important. And a lot of places, they will try to burn you out. I won't name any names. But if you find a good research group, or you can found a good research group of really collaborative people who are there for the same person, you can do amazing things.
Yeah,
And do wonderful research together and support each other, socially and scientifically if you so choose.
yes.
Um,
It's what they say
and it's the
about
kind of thing that
teamwork.
definitely makes a big impact.
Yeah, absolutely. Keeps people in the field as opposed to taking a break and never coming back.
Yeah, or burning out and never coming
Yeah.
back, which does
Hmm.
happen as well. And that's something, it's like, hey, if you can get involved in a good supportive program, it makes all the difference. And
Absolutely.
of course, the fact that he was also involved with white dwarfs and subdwarfs, and many, many kinds of stellar types, most of which had not yet been identified. Subtypes of star, that really set the stage for so many different things.
Yes, like our next piece.
It does. So speaking of subdwarfs, that's going to get me to my next cheating this week in space and astronomy history. So subdwarf stars were another one of my own personal favorites. Entirely biased, I might add, because I got to go observe them a lot. And I'm going to go back to October 21, 2002. And this paper came out on the origin of subdwarf B stars. And it's literally called The Origin of Subdwarf B Stars. And the paper that came out on October 21st, 2002 was just a slight variation. The origin of subdwarf B stars, one, the formation channels. This was published in monthly notices by Zihan and a few colleagues, who unfortunately I did not get to work with. But subdwarf B stars are a really strange beast, and this is something that, of course, Greenstein would have noticed, obviously did notice, and a lot of other people have found out as well. Is once you start getting into stellar spectrum and trying to understand what stars are really doing, the regular classifications, O, B, A, F, G, K, M, they just don't get you very far because most stars are really individuals and they have a lot of things going on with them. You can have stars that are B stars, but they're not B stars. They might have had something happen to them. And subdwarf B stars are small, hot stars that have a really high surface temperature and low luminosity. And I just would invite everybody to imagine something. What makes something hot and small? um, and if you're already thinking about white dwarfs, you're actually kind of thinking in the right direction because you're thinking about cores of stars. So these subdwarf B stars are stars that used to be big. They used to be B stars. So B stars are like O stars are the really, really big ones, and B stars are right next to that. So they start off as very, very large beasts, but something has happened. Something has caused them to lose most, if not all, of their outer hydrogen layers. What could it be? It's a mystery. So you get these stars that are basically just exposed helium cores. So if you have a regular O or B star, what you have is it's a bunch of hydrogen that collapses in on itself in space. And of course, the middle starts to go and have fusion. And if it's a massive star, you get the CNO cycle. You get crazy hydrogen, helium, carbon, neon, oxygen atomic reactions happening in the middle. So your massive stars, that's what they do. They've got big bunch of hydrogen, which is in the process of very, very rapidly making other elements. But if something happens to it, something sneaky or disastrous, or a white dwarf that gets way too close and starts to orbit inside its you know outer layers. Things can happen. Um, so something happens where the outer helium uh, is the last layer. So all that hydrogen that would normally be on the outside, making it a giant star, has gone away. And all you have is the core underneath, which means, of course, you can get very, very good direct observations about what a helium core looks like if you watch enough of these subdwarf B stars. It's really cool. They totally oscillate. They do really fun things. There's different pulsational modes that actually tell you things about how the insides of these massive stars operate. But they're obviously also quite a mystery. So the paper, the origin of subdwarf B stars, the formation channels, I did not get it to be on that paper. I was not at that time famous enough, but at this in October 2002, I was actually observing as many subdwarf B stars as I possibly could every single weekend on telescopes in Arizona. And that was a I want to say mostly unpaid undergraduate position. Um, I was probably making a bit less than some of than our current work study students over at the Allan Carswell Observatory, but I got to do a lot of observing and become certified on some of those telescopes, and that was actually the certifications still help me today. Because when you're out observing a lot of stars, you get a lot of experience about how those observations work. And when you go to reduce the data on those stars, you'll know how important various types of calibrations are. And so the subdwarf B stars that are hot, dense objects in space, these interesting little mysteries. It's thought that some of them would have had a binary companion at some point, but a lot of them are actually found today with no companion. So something in their interaction, maybe around the time it lost its outer layers, might have led to the companion being ejected. And the companion as a white dwarf means, of course, that if you're going to look at subdwarf B stars, you also need to make sure you look very, very carefully at the spectrum of white dwarf, just in case it's a binary that's too close to be resolved, in which you get sort of everything mixed together. You'll have to be able to try to sort of separate out which components are due to white dwarfs and which are not. So it's kind of fun, of course, because obviously this week in space and astronomy history, I was out observing these things, and this paper came out around the same time. And they are basically little sort of cosmic laboratories. And I would go so far as to say all stars are cosmic laboratories. However, subdwarf B stars in particular really offer insights into very specific kinds of stellar evolution and binary star dynamics. Because if you have two stars, it is more than twice as complicated, and they can do all kinds of interesting things. There are many peculiar processes leading up to the loss of stellar envelopes and interesting characteristics that sort of go against models. So there's a bit of a contest going on, can we model these systems? How well can we model these systems? And what observations can we find that don't fit the models or that do fit the models and therefore confirm them? And so you have a constant sort of a cycle of models being confirmed and then disavowed by one observation later. It's great fun if you like that sort of thing. So it's of course also related to the basically the life cycle of the stars and therefore the life cycle of the universe. And it's a little bit interesting that as well, I did see a note, I think, about, I'm not sure if this was Greenstein or somebody else. Greenstein did Upsilon Sagittarii. And of
Yes.
course, when you said Sagittarii, I immediately thought of the Sagittarius dwarf. But this is Epsilon Sagittarii is actually directly related to the subdwarf B stars because it itself is a very, very unusual helium star. So hydrogen is the thing that everything was made out of. To get a helium star, you wouldn't just have to lose some of your outer layers, you would have to lose literally all of your hydrogen, like
Weird.
everything. You'd have to get rid of all of your hydrogen layers. And how would that happen? How could you possibly get rid of every single trace of hydrogen out of a stellar core? So they're very rare. I think there's only been a few, like 3 or 4 found. But Upsilon Sagittarii, I would go so far as to say, is probably the closest Greenstein object to a subdwarf B star, which actually I did not know until I looked it up for this episode. So it turns out, if you start studying stars, you find out all kinds of cool stuff.
Very neat. Yeah. We keep trying to put things in tiny little boxes and it keeps not working.
Yeah, things are always more complicated, always less linear. There are always individual cases. And if you go to understand a system, you need to try to understand not just its environment, not just its own statistics, but also its history and what could have happened, before. And the fact that white dwarfs play such a major role in creating a lot of these really interesting stars, potentially Upsilon Sagittarii, although I know that's controversial, but also many, many subdwarf B stars, means that until you understand white dwarf stars, you actually have no chance of understanding a huge number of binaries.
Yes. Well, speaking of white dwarfs,
Speaking of understanding white dwarfs,
speaking
absolutely,
of
yeah.
understanding white dwarfs, our next topic, or person, the subject of our next item is Subrahmanyan Chandrasekhar, who was born on October 19th, 1910. And he was a theoretical physicist who made significant contributions to the knowledge of stellar structure and evolution and black holes, eventually winning the Nobel Prize for Physics in 1983 with his PhD advisor, William A. Fowler, for, quote, theoretical studies of the physical processes of importance to the structure and evolution of the stars, end quote. A list of concepts and institutions and instruments and et cetera, as long as your arm are named after him. So I'm not going to list it here because we'll be here all night. He worked on a wide variety of physics and astronomy subjects, including stellar structure, white dwarfs, stellar dynamics, stochastic process, radiative transfer, quantum theory of hydrogen anion, hydrodynamic and hydromagnetic stability, turbulence, equilibrium, and the stability of ellipsoidal figures of equilibrium. I don't even know what that means. General relativity, mathematical theory of black holes, the theory of colliding gravitational waves. This guy was just really into physics and math and astronomy, and apparently always thinking about it. So as mentioned, he was born on October 19th, 1910 in Lahore, in what was then British India and what is today Pakistan. His family was Tamil. His father, Chandrasekhar Subramaya Iyer, was stationed at Lahore as Deputy Auditor General for the Northwestern Railways at the time. And he was the third of 10 children. His paternal uncle was the Indian physicist and Nobel laureate Chandrasekhar Venkata Raman. So he was from like a fairly um privileged family in India, although I mean still under British colonialism. His mother, Sita Krishnan is credited with arousing his intellectual curiosity. And the family moved to Allahabad in 1916 and then to Madras in 1918. Chandrasekhar was homeschooled until the age of 12, with his father teaching him math and physics and his mother teaching him Tamil. He attended the Hindu high school before studying at Presidency College, which was affiliated with the University of Madras, obtaining his honors BSc in physics in 1930. He won a Government of India scholarship to do graduate studies at the University of Cambridge under R.H. Fowler. And during his travels to England, he spent his time working out the statistical mechanics of the degenerate electron gas in white dwarf stars, providing relativistic corrections to Fowler's previous work, as you do, apparently, while you're on a boat ride from India to England. His time at Cambridge reads like a who's who of physics and astronomy. He worked and in some cases feuded with big names and at various institutes in Europe. And he earned his PhD in 1933 and was awarded a prize fellowship at Trinity College for the period of 1933 to 1937. Chandrasekhar was invited by Harlow Shapley to be a visiting lecturer at the Harvard Observatory in 1935. During the visit, he was offered a research fellowship there, but he turned it down. In 1936, he was offered a faculty post at the Yerkes Observatory, which is run by the University of Chicago, which he initially turned down, but eventually accepted. And he spent the rest of his career at the University of Chicago, where he became a full professor by the age of 33.
Wow.
Yeah, I know, right? Um, he got his American citizenship in 1953. Chandrasekhar's career could be divided into distinct periods because of the way he studied things. He would like do a deep dive, write a bunch of papers, write a book, move on to the next thing. So from 1929 to 39, he studied stellar structures, including theory of white dwarfs. And then from 39 to 43, stellar dynamics and Brownian motion. And then from 43 to 50, he moved on to radiative transfer and quantum theory for negative ion of hydrogen. And then during the 1950s, moved on to turbulence and hydrodynamic and hydromagnetic stability. And then in the 60s, moved on to the ellipsoidal figures of equilibrium and general relativity. In the 70s into the early 80s, was looking at the mathematical theory of black holes. And then the late 80s through the end of his career, the collision of gravitational waves. Among his doctoral students is Canadian astrophysicist and Barbara Underhill, who we'll have to talk about some other time, but she seems really cool from what little I had time to read about her. He died of a heart attack on August 21st, 1995, and was survived by his wife, Lalita, who lived to be 102 years old. And they'd met back in their undergrad days, where she was a student of literature and Western classical music.
Wow. All as you say, all in all, very, very accomplished. And of course, without Chandrasekhar, we don't have the white dwarfs that we know and love from binary systems or all kinds of things. But substantial contributions in other areas as well.
Yeah. Um, it, I was listening to the Smithsonian's Side Door podcast about him, and sounded like he and Sir Arthur Eddington,
Yes.
I won't say they didn't get along, because apparently he's quoted as saying he considered him a friend, but like they did not
Uh,
agree about black
yeah, they had
holes.
some maybe vigorous debates would be the nice way of putting it.
it sounds like it sounds like, you know, oh, and then they would go into this lecture theater and just rip each other apart. I'm like, that does not sound like an encouraging way of doing science.
Yeah, yeah. Well, and there's definitely I don't know, there's a whole group that sort of goes by that kind of motto, I suppose, is defend your science, but like really to vigorously defend because you will be attacked.
Oh, yes,
And
sure.
if your
Be
science
able to
holds up to
defend
the
your
attack,
science
then you should,
and like
yeah,
answer the questions and like know your stuff, but
yeah,
like calling it astronomical or cosmic buffoonery, like
yeah.
I feel like that crosses a
That's just
line.
being insulting.
Yeah. Like now you're just,
There's no need
attacking
for
the
that.
foreigner.
Yeah, well, and I mean, of course, they did have the pretty famous debate as well, and of course, Chandrasekhar was proven correct in
Yes.
time.
Yes,
Um,
he was.
but you have to really admire as well because this is somebody who had to stand up against a major high level power player, and I mean, he obviously had allies, but to all intents and purposes, he was standing up by himself
Yeah.
with his science and prevailed. And I'm always just in admiration of that. It's like somebody who was like, no, I have the science. I'm not backing down. And I'm
Yeah.
like, yes, thank you. That's amazing. You're
Yeah,
awesome.
because I'm sure many people would have been like, okay, this person who I look up to as like one of the big people in my field has just attempted to like completely discredit me. I'm gonna go hide in a
Yeah,
hole
well,
now.
and going so far as to openly criticize and belittle someone else just because you don't agree with them, that's not scientific. That's just being uncalled for.
Mm.
So Eddington does not do well in this particular comparison because it's like, yeah, that was really uncalled for, not scientific at all, and it just goes to show that like if you do have, even if you have your science and you are Chandrasekhar level smart, um, people, Eddingtons, might still try to just burn you down. And it's that's where it becomes very important to have those, be able to defend yourself and get those allies because he did prevail eventually, but it couldn't have been pleasant. No.
No, no, definitely not. All right.
We're
Um,
we're all on the Chandrasekhar side here. I think it's safe to say
yeah. Yeah.
because it's like, oh yeah, and a lot of this was recorded, but I can imagine that a lot of it wasn't too. So,
Right. We have a few reminders this week.
oh yes, we do. It's a bit past halfway, but we'll do the reminders. Just as a reminder to everyone who is listening anywhere near October 21st, the observatory tour is back on this Wednesday. Or actually not this Wednesday, but next Wednesday, sorry. Actually, am I telling two lies? What day is it? It's October 21st.
Today is the 21st. Wednesday is
It's
the
going to
23rd.
be, it is going to be the 31st. The 31st. So it is a double lie because I actually put it into the show notes wrong. There is a special tour Halloween October 31st, which is on a Thursday, not on a Wednesday. So if you're trying to come to the in-person tour at the observatory, don't get confused like I just did. Special Halloween tour on October 31st is the Thursday, which means that that week there actually won't be one on the Wednesday. And we have a high school teachers night coming over this week, so we're actually not doing a tour. So if it's not on the website and you don't have tickets, don't come. The other notes
Good
are just
advice.
watch our website regularly for updates at the end of this month, yorku.ca/science/observatory. we will be doing a fundraiser to try to raise some funds for observatory operations. You'll be able to donate through the donate button on the website, and there will be cool stretch goals and prizes. I should say giveaways when goals are met. So
Fun.
that's all the reminders fit to print.
All right. All right, let's move on to news. We still have a little bit of time.
Yeah, I did. I think we both got star related ones, and they're very timely as well. I just have
Mhm.
a little bit of a fun one. For stars, I had to put in there this really fun one for Gliese 22b. Gliese 22b is an interesting star system that has been, you know, basically uh, watched for quite some time, and it's sometimes called a failed stars, made up of a brown dwarf and another brown dwarf. They were orbiting so closely that it actually took a whole 29 years to tell that it's actually two stars and not one. Uh,
Yes.
so it's the first of its kind that we know of. So the first ever confirmed, very, very tight, close together, two brown dwarfs in a binary. And it's an extremely exotic system, to say nothing of unusual. Brown dwarfs themselves are always a bit of a mystery, but this particular system, it's 229b. If you're interested in typing it up and looking for more information, it is always been strange because it always looked like it was too dim for its mass. Brown dwarfs are the dimmest kinds of stars. They're the lowest mass. They have extremely long lives, and they're very, very, very hard to find. I think it is very, very safe to say that we do not know how many brown dwarfs are out there because we absolutely cannot count them. They are too faint. They're just very, very hard to see. But having this one all this time be a little bit of a mystery, why is it so dim when its mass seems to be higher than it should be? And it was actually considered for a long time to be the typical brown dwarf star. It was sort of like, okay, this is our poster child brown dwarf. It's only 19 light years away. It was one of the first known brown dwarfs, and introduced the concept of failed stars. And it turns out it was not a single star at all. It actually was two stars. They were just so close together, we could never tell until our telescopes got to where they are now. So they are now called 229BA and 229BB, just because we're bad at naming things. They're separated by 3.8 million miles or 6.1 million kilometers, which might seem like a lot, but it is only 16 times farther than the Earth and the Moon. So it is very, very close for two stars. They are so tightly bound around each other that they actually whirl around each other about once every 12 Earth days. So the year, such as it exists for them, is only about 12 days long. So they think it isn't a single object now. So they used to think it was a single object with 70 times the mass of Jupiter. But now they think, aha, we've pinned it down. We think we know what it's doing. It's one brown dwarf with 38 times the mass of Jupiter, and another one with 34 times the mass of Jupiter. So this is a very big, fun mystery as well. How could you possibly get two brown dwarfs orbiting each other that closely? And I think I'll leave it as a little bit of a mystery because we don't know the answer to that. So your guess is as good as mine. Please feel free to comment on the video or in the podcast. Um, and if you're interested in the sizing, it sort of puts the brown dwarf, it's basically going to be in between the mass of Jupiter and our own sun. This kind of missing link between stars and planets. They have been theorized both in science fiction and in science since the 1960s. There's some very fun stories out there. But it wasn't until they actually found the first one in 1995, which was, of course, Gliese 229b. And they found methane in its atmosphere, or I should say, one of its atmospheres.
Oh,
Yeah, it is a very fun system, and now we know it is too. So it just goes to show, even if you think you have the stereotypical example of something, you could still be wrong, and it will be awesome.
okay. So you have the star,
Hmm.
Gliese 229A.
Yep.
And then we thought there was one thing going around it,
Oh, no, no,
but it's
no. So we
actually
thought we thought
two
it was
things
one
going
star.
around it.
So it's just two stars as far as we can tell.
Okay.
There might, if there are planets, that will make it more complicated. So right now it's Gliese 229 b is what they thought was one object.
Right. But that's going around Gliese 229A, no?
No, it's going around Gliese 229 ba.
Well, because they're
What
going around, yeah. BA and
it's
BB are
exactly
going around
so,
each
what they've
other.
done is they've split it up. So it was Gliese 229b, and now
Yes.
they've split it into Gliese 229 ba and Gliese 229 bb.
Okay. This illustration that I found is totally confusing me because there's like these two things going around each other, but there's also like a bright star in the background. And I'm like, are they orbiting this star?
No,
No. So
not
they're just on their own,
they're on their own. They're
orbiting
on their
each
own.
other.
Don't
Okay.
remember, the artist's impressions can be very, very wrong.
Yeah, clearly.
um,
Okay.
but
I'm
yeah,
gonna have
it
to
is
read more
there are
clearly.
two stars orbiting each other, and there could be more things in there. We just haven't
Yes,
found them
okay.
yet.
Two not quite stars orbiting each other.
Exactly.
Gotcha. Okay. Just on their
Speaking of
own,
stars,
all alone in the night.
yeah.
Um,
Um,
that was a little Easter egg for folks out there. Um, all right. Okay, so we've got 3 minutes. I want to get this in here because
oh
it's
yeah,
big.
it's very
Um,
big.
yes, we are officially at solar maximum, people.
Yay!
NASA, the National Oceanic and Atmospheric Agency, or NOAA, and the Solar Cycle Prediction Panel have made it official. The sun has reached its solar maximum period. This was announced last Tuesday, October 15th. In case you don't know, a solar cycle is 11 years long, and during that 11 years, the sun transitions between a period of low activity to high activity. At solar maximum, the sun's magnetic poles flip and it becomes active and stormy, releasing light and energy and solar radiation into the solar system, what we know collectively as space weather. Space weather can affect satellites and activities in space. Here's looking at you, ISS, as well as communication systems and power grids, but also Aurora.
Yay!
Yeah, the sun has outpaced predictions, and we've had lots of pretty displays in recent months. But if you have missed them, don't worry. Solar maximum as well as lasts 2 to 3 years. So keep an eye on those aurora predictions and keep an eye on the sky.
Oh yeah, absolutely. And I mean, it's be interesting to see how long it does last. But I personally only saw the tiniest little bit of aurora, so I would really like another chance.
I'm assuming you got clouded out in May and just saw a little bit last Thursday.
Yeah, basically, just the tiniest bit. And even when I went out to dark skies, I couldn't see any. But I did manage to get a little tiny piece in my backyard in downtown Toronto, of all places.
Nice.
And that's the closest I've gotten so far. So I am still holding out that next summer at Killarney Park will be
Yeah.
Aurora for all of us.
Yes. I went for a drive on Thursday, but I zigged when I should have zagged. There's a lake north of me. I went east. My colleague went west. She got beautiful pictures. I got a little bit of something. I saw something. It wasn't as awe-inspiring as other people's were, but it was exciting nonetheless.
Yeah, and I mean, it's like, okay, well, you still saw it, so
I still saw it.
but I'm still holding out hope for next year as well. And it's a handy reminder to folk that Astronomer in Residence, it will also be happening next year, so stay
Yes.
tuned.
Yes. All right, everyone. You have been listening to York University Astronomy and Astrophysics
Well, it's like,
program,
okay,
written
well, you still
and
saw it, so
presented
I still saw
by the
but I'm
students,
still holding out hope for
faculty,
next year as well.
alumni, and
And it's a
friends
handy reminder
of
to
York
folk that
University.
Astronomer in
The
Residence,
hosts
it
this
will also
evening
be
have
happening
been
next year,
myself,
so
Judy
stay
Tomei,
tuned.
and
Yes.
Dr. Elena Hyde. All right, everyone. You can always connect with us on Instagram with the handle
Well, you still
at
saw it,
York
so-
Observatory
By
and
But I'm still
Facebook
holding
at
out hope
Allan
for
I
next year
Carswell
as well.
Ops. Check out our website for show notes,
And
content,
handy reminder-
updates, and contact info at yorku.ca/science/observatory.
All right, everyone.
Thanks for tuning in to York Universe. Clear skies and have a good
Allan
night.
I
Carswell
Carswell
Ops. Check out our website for show notes,
And
content,
handy reminder-
updates, and contact info at yorku.ca/science/observatory.
All right, everyone.
Thanks for tuning in to York Universe. Clear skies